Hi, in this video we will discuss the conditions which guarantee that a function is integrable. So far we have seen the definition of integrable functions, but as you may have noticed, this is very cumbersome and heavy computationally definition. Who's going to find all the Riemann sums with all sample points and find the limit and check that they have same limits? It is impossible. There is no way that one can do that. This means that we need theorems and new theories and tools that gives you some conditions that tells, okay, if your function has this condition, then it is integrable. One of these theorems, which is very important for us, is that if a function is continuous on an interval AB, or it is not continuous, but it has only finite discontinuity points. So, or if it has only finite discontinuous points on the interval AB. So if it is continuous or it has only finitely many discontinuities, then f is integrable function on the interval AB. You don't need to do anything else. As soon as you know the function is integrable, is continuous, or has only finitely many discontinuities, it is going to be integrable. You don't need to go through the definition, find Riemann sums, and find the limits, which is impossible task to complete. Well, as an example of these things, now you don't need to check that the function f of x equal to x squared is integrable on the interval 1 to 3. And the same goes with the function f of x equal to 2 to the power 2x plus 3 on the interval, actually on any interval, specifically in particular 0, 1. You can also have a function which has finitely many discontinuity on the interval. This greatest integer function, remember, it has only discontinuity points on the integer points, so it is going to be integrable on any finite interval, for example, from -1 to 2. Even functions, strange functions like f of x equals to sine of 1 over x, when x is not 0, it is continuous on all those points. At x equal to 0, it is not continuous. This guy is still integrable on any interval AB. Yeah. So these are just, we didn't do anything, just use the theorem if we guarantee that yes, it is integrable. But this theorem has also another implication which is very nice and will help us not only see it is integrable, but find the value of the integral with less pain. So on the other hand, the theorem tells us that no matter what sample points you choose, no matter what sample points xi star you choose, the Riemann sum, the limit of the Riemann sum, the limit of sum is going to be equal, is going to so no matter what sample point you choose, these are going to be the same when the function is continuous. So let me just add this condition: when f is continuous. So you don't need to bother choosing different sample points. Just go choose one very specific one. Remember that we have used it in the area problem. And well, if you choose the right endpoint, this is, remember we called this one Rn, and then find the limit of that as n goes to infinity. This guy is going to be your definite integral f of x dx from a to b. Or you can do the same thing with the left endpoint approximation that we use in the area problem. Yes, so you found just this sum, evaluate that, and let n go. Oh, these are not up to infinity, these are up to n, sorry. So you find those sums and evaluate them and find the limit. The value you find are going to be the value of the definite integral. Well, remember that we have done some of these examples that the function f of x equal to x squared from 1 to 3 dx. We have found this. This is positive function, and when we were doing the area problem, we found Rn of this function, which is, well, this is going to be 2n 1 plus 2in squared, I going from 1 to n. We actually found an explicit formula for this. Go back, check the videos that we had before. And actually we found the limit of Rn for this case, and the value was 26 over 3 as n goes to infinity. Now we know that this value must be equal to the value of the definite integral 1 to 3x squared dx, and we found it already. Yes, knowing that x squared is continuous, we don't need to be worried about different sample points. Just pick the right endpoint or left endpoint as sample points and go ahead, you will complete that. The other example that we completed before is 0, 1, 2 to the power 2x plus 3 dx, and we know that this must be equal to right endpoint approximation of this guy, and then we had limit of sum 2 to the power, I have 1 over n, 2 to the power 2 times I over n plus 3, I going from 1 to n goes to infinity. Again, if you don't remember, go back to the videos and you will see that we computed this value, and the value of that is 24 over ln 4. So this way we have found a way just to go around that strange definition of all Riemann sums having the same limit. And you can compute definite integrals using this right endpoint approximation, or limit of right endpoint approximation.